Here we're going to revisit gradient fields. We saw those earlier, and we're also going to look at a new sort of field called a curl field. So first let me remind you a little bit about gradient fields. So remember that one way to evaluate a line integral is to evaluate a potential function at the end point and at the starting point of the curve C and take the difference of those two things. So notice that implicit in that statement is that in fact there is a potential function. So if there's a potential function little f, that's a scalar valued function, then we have a nice way to evaluate line integrals. And remember that the connection between little f is that its gradient is equal to the vector field. Okay, so let's keep talking about gradient fields. So remember from a previous chapter, we know that the following things are all the same. If one of them is true, they're all true. So f is a gradient field if there exists a scalar potential function f such that the gradient of little f is the vector field big F. The vector field f is path independent, so any line integral in this vector field is going to be the same provided I go from one point to another point. It doesn't matter how I get there. So if I go from that point to that point, it makes no difference whether I go that way or straight there or some other way. If the vector field's path independent, the line integral along all those paths is the same. Also, so the idea is actually pretty simple. If f is a nice vector space, so again, this essentially means that its pieces have nice derivatives and it's defined everywhere in the region that I'm interested in. Okay, so if f is a nice vector field, and if the curl of f, and now we're talking about the 3D curl, the vector curl is the zero vector, so it's important to remember that this is the 3D curl and not the 2D curl. If we have those two conditions, then we can apply Stokes' theorem. So Stokes' theorem says that the line integral around a closed path that's associated with the surface S can be evaluated by taking the flux integral of the curl of that vector field f. Well, if this curl is always zero, then I simply am taking the flux of the zero vector field, and of course, through any surface, that's going to be zero. So, as long as f is nice everywhere, then no matter what the path is, this line integral is always going to be zero. Okay, so and in particular, any closed path line integral will be zero. So the integral around C of a closed path is always going to be zero, and this is for all C. Okay, so if all closed path integrals are zero, then f is path independent and f is a gradient field. I really want to emphasize that it has to be for any and all closed paths. Okay, so I get that f is a gradient field. So the upshot is that if the curl of f is equal to 0, then f is a gradient field. Just as in the previous chapter, but now we've extended it to 3 dimensions. Here's a simple example of applying the curl test in 3 space. So here's a vector field, and I'd like to know, is it a gradient field? That is, can I find a scalar potential function? Well, so I'll apply the curl test. I'll take the curl of f, and this time it's this 3D vector curl, so I take the determinant of this mess, and you can pause the video and make sure that I did it correctly, but it looks like the curl of f is in fact the zero vector. So what that tells me is that yes, f is a gradient field. And in fact there exists some scalar function little f such that if I take the gradient of little f, I should get the vector field f. And in fact, I don't think it's too hard. If you just look at it for a little bit, you'll see that this scalar vector needs to have an xyz. So notice when I take the derivative of that with respect to x, I'll get yz. So it's certainly going to have that piece. And then in the other two pieces, I notice that there's a z squared and a 2yz. So I think there's going to need to be a plus yz squared piece. So then I should just check. If I take the derivative of this with respect to x, I'll get yz. If I take the derivative of this with respect to y, I'll get xz plus z squared. And if I take the derivative of this very same function with respect to z, I get xy plus 2yz. So there, in fact, is the scalar potential function for this vector field, and then I can use that to evaluate line integrals.